Hello everyone. Today on our Grad Talks seminar, we are having Dr. Stefano Papirio'ya. He is from the University of Napoli Federico II, from Sanitary and Environmental Engineering Department. He received his PhD in Civil Engineering, and he is teaching some courses including wastewater treatment plants and mitigation of climate change. He has an extended international experience in several foreign institutes such as UNESCO, IHE Institute for Water Education, which is in Delft, the Netherlands, and Tampere University of Technology in Finland and National University of Ireland, Galway. He coordinated 2 European international doctorate programs, and he is now the principal investigator of COMED project, founded within the MED program. What does that stand for? ENI
CBC.
ENI CBC
yeah.
MED program. He has co-authored more than 100 scientific publications in peer-reviewed journals and national and international conference proceedings. So, thank you, Stefano, accepting our invitation. We are pleased to have you in our seminar, so you may start your seminar. Thank you.
Thank you. The same for me, and thank you, Bestamin. Thank you, Murat, for inviting me and giving me the opportunity to give this talk on this topic that I find really interesting, because it is part of the research of some PhD students that we had within one of these joint doctorate programs that you were mentioning, and it's also actually part of the research of another PhD student that I'm following together with some colleagues from National University of Ireland, Galway. So the title of the presentation, as you can see, is Strategies to Enhance the Biomethane Potential of Lignocellulosic Residual Feedstocks. So, just to give a very broad introduction, but quite brief. Of course, our world is nowadays facing some major challenges. Maybe you have seen lately there is a new documentary in Netflix which is called Breaking Boundaries. So one of the major scientists of climate change, who is Johan Rockström from Sweden, proposed this kind of theory of the quadruple squeeze, where he says that there are 4 main driving forces which are kind of pushing out our planet from its stable state, which is the era that we are living now, the Holocene. So the main driving force which is pushing out the Earth from this stable state is the population pressure. So population pressure, because of population growth, is negatively affecting a lot of aspects of our planet. Is affecting climate, and so we are actually seeing an important change of climate. We have been seeing this for 20, 30, 40 days mainly. Of course, it's affecting the environment, and we are basically talking about this aspect today. And it's affecting, of course, the food, energy, water nexus. So the supply of clean water, of fresh water for agriculture, for drinking purposes, for industry, whatsoever. The supply of energy. And so we are also talking about energy today, and the supply of food. Because, I mean, we are committed to be 10 billion people in 2050. And at the moment, actually, a lot of research is going in the direction of finding new sources of food to provide food to this increasing population. So what we have to do as environmental engineers, one of the main, challenges of environmental engineering today is actually to switch from a model which is a linearly based model, so based on a linear economy approach model, to another model which actually entails the recovery of resources from, for example, wastes and wastewaters, and actually promote the production of new sources of energies which have to be sustainable and renewable. So I'm using the pointer, which is better. Yes, okay. Of course, if we want to move towards a more sustainable world, we should actually consider to develop some new strategies. We have been listening a lot nowadays of biorefinery strategies. So actually those processes related to the production of biofuels, biocommodities, by biological processes, or starting from biomasses. And what we think is that anaerobic digestion, which is a biochemical process that maybe all of you knows already, has to be still the core of all the biorefinery strategies that have to be developed from this moment onwards. As you know, anaerobic digestion is a biological process, or biochemical process, which occurs through different phases. We start from complex organic matter, and we, as environmental engineers, normally use some residual feedstocks, residual substrate that can be sewage sludge, municipal waste, such as organic fraction of municipal solid waste, landfill waste, or agricultural residues, such as lignocellulosic, manure, and energy crops, and convert this complex organic matter through a pathway that goes towards the formation of a biogas, which is mainly constituted by methane and carbon dioxide. As you can see, I'm sorry if some of the writings here are in Italian, because this is actually a flowchart of the use of fuels that is expected to be in Italy, but is very, very similar to all the flowcharts that you can find in the decarbonization strategies of different countries. In 2050, as you know, the European Green Deal and the commitment of all the countries within the Paris Agreement on Climate of 2015 says that we want to reach carbon neutrality by 2050. And to do this, of course, the share of energy that we need for civil purposes, transportation, and industrial purposes has to come from renewable sources. So, geothermal, hydroelectric, wind, solar, biomasses, such as lignocellulosic materials, the ones we are talking about today, biogas, okay, and green fuels and biofuels mainly. As you can see, other fuels, this is written in Italian, okay, but this means other fuels and natural gas will only be a very, very small percentage of the share for the production of energy in 2050. And as you can see, apart from biogas, green fuels, and biofuels, all the other sources of energy undergo a process that converts energy into electricity, and then electricity is the main source of energy that is provided for civil, transportation, and industrial purposes. So we can invest a lot still on biomass and invest a lot of biogas, because they will, based on the decarbonization strategies that was prepared and proposed by the Italian government, will represent about 20 or 25% of the share of energy in 30 years. And as I was saying before, this is actually quite important, because is reported within the major programs that European Commission, but also the other countries worldwide, are putting in place, like the European Green Deal that promotes the use of energy from renewable sources, and establish that the goal of reducing the greenhouse gases emission by at least 55% has to be achieved by 2030. So we have only 9 years to achieve this target, which was set by the Paris Agreement, so by all the countries that approved the Paris Agreement in 2015. We have a more ambitious objective by 2050, which is the carbon neutrality. So what we emit has to be balanced by the carbon sinks that we have on our planet, which are mainly oceans and forests. And regarding energy, at least 30% of the EU energy needs has to come from renewable sources. by 2030. And 55% of the electricity production has to come from renewable sources. So these are quite challenging objectives that EU can anyway achieve because it's in a very good trajectory so far. And biogas still plays an important role. So what are the estimations? The estimation is that biogas has to increase in terms of production and gradually rising from 1.5% to 6.87% in 2030. So the share of energy has to increase. Okay, here it's only for the transportation sector, but if we consider also the civil sectors and industrial sectors, this share has to increase to 15, 20, 25%. And the sources of biogas have to be mainly wastes or residues or feedstocks, and always less of this biogas has to be produced from those sources which are known as first generation sources that result in the production of first generation biofuels, because as we can see later, the first generation biofuels have a main shortcoming, which is the competition with feed and food targets, feed and food production targets. Okay. So what is the situation of biogas in Europe? This actually is a picture of 2018, but can also actually be considered as the modern situation because has not so much changed in the last 2 years. So we can see that number of plants is very, very high, especially in some countries such as Germany, which has something like 11,000 plants aimed to biogas production through anaerobic digestion. Italy is at the second place, with roughly 1,700 plants installed on the national territory. And where this biogas, so where is this energy coming from? It's something we can appreciate here in terms of installed electric capacity, so in megawatts. We can actually see that biogas, okay, comes from mainly agricultural residues. Why? Because agricultural residues are mainly, as we saw in the previous slides, lignocellulosic materials, manures, other crops, which embed a high amount of carbon and nitrogen within their matrices. And so if we are able to kind of extract this carbon from these residues, we can actually gain a lot of energy and a lot of biogas if we are able, of course, to perform properly the process. So that's why here I was actually writing power to plants and animals, because the residues from plants, so agricultural residues, and residues from animals, mainly dungs and manures, are perfect substrate that we can use for anaerobic digestion purposes. Well, it is not actually true that lignocellulosic materials are perfect substrates for anaerobic digestion. They are suitable, but they are not perfect, because we have a lot of advantages if we think about the use of lignocellulosic materials for anaerobic digestion. And the advantages are mainly reported here, and they are indicated with this green arrow, because lignocellulosic materials are largely available on the planet, because we account for approximately 3 billion tons of agricultural residues produced yearly worldwide. They are relatively inexpensive because lignocellulosic materials are what remains from crops, like, for example, wheat, like, for example, rice, sorghum, and also what remains from agri-food production, for example, shells of hazelnut, of walnuts, of almond, or skin, or, for example, what remains from the industry of coffee, as we will see later. And so, being wastes, we can actually get them for free, or their cost is very low, so they are particularly cheap to be used in our applications. They are then sustainable. Why they are sustainable? Because we can say that the anaerobic digestion or any kind of valorization of these materials, like for example also pyrolysis and gasification, is a carbon neutral technology. Because if we consider, as I said before, that these materials derive from plants that previously grew and captured CO2, now we are actually promoting the valorization of these substrates for energy purposes. And if we are releasing CO2, we are basically releasing the CO2 that was previously entrapped by these materials when they grew as plants. So the balance in terms of CO2 is zero. So we can actually say that it's a carbon neutral technology. Why I'm talking about also pyrolysis and gasification, because chemical engineers, compared to us environmental engineers, tend to valorize these substrates with thermochemical processes such as pyrolysis and gasification, because as we can actually appreciate from these slides, the main feature of these materials is that they have a very hard cortex, mainly composed by these three polymers, which are cellulose, hemicellulose, and lignin, which render the material quite recalcitrant to microbial degradation. So as we will see in a while, in order to biologically valorize these substrates with an anaerobic digestion process, we need first to transform the structure of these materials and then apply a biological process in order to enhance the biochemical methane potential of these materials. But another advantage that they have compared, for example, to energy crops, which are the sources of those first generation biofuels, is that they do not threaten the food supply, because we are not actually planting plants which go in competition, okay, for arable lands, so for land use, with the crops that are used for feed and food production. And this is good because, I repeat, this is the leftover, I mean, a lignocellulosic material is a leftover, so what remains from the cultivation of some crops, okay? So, in order to increase, in order to improve or enhance the extent of the products that we want to get from the lignocellulosic material, we need to pre-treat these materials. A pre-treatment is a treatment that is done prior to anaerobic digestion. So we need to somehow modify the structure of this material in order to gain a higher amount of the product that we want to get from these materials. In this presentation, I'm only talking about biomethane, so our product is biogas. In order to get a higher amount of biogas from these materials, we need to modify the structure of these lignocellulosic materials. Why? Because if you see the structure of this material, you can actually see two layers here of lignin. Then there is hemicellulose here, and then all these fibrils is cellulose. So potentially, this material is can be valorized towards the production of biogas, but the structure is so hard and is so harsh towards the microbial attack, so the enzymatic activity of the microorganisms, that if we undergo this material directly to an aerobic digestion process, the yield of our process in terms of, for example, biomethane potential would be very, very low. So we need to make something to this material in order to make the work of our microorganisms during anaerobic digestion easier. So, and on what parameters we can actually intervene? These are the main parameters that we can somehow modify when we use treatment to modify the structure of our lignocellulosic feedstocks. And the parameters are cellulose crystallinity, because all these orange fibers that you see here are quite ordered. And if we can somehow make a bit of disorder inside these fibrils, we basically allow the microorganisms to fit better within the material, okay, and valorize a higher portion of the material towards biomethane. A similar concept is related to the accessible surface area, because if we increase the area that microorganisms can attack, we have higher chances to get a higher production of methane. And finally, if we reduce lignin content, so if we basically disrupt the main barrier of the material, we also in this case make the life of our microorganisms much easier, because they can enter easily inside the material and start degradation of the polymers contained in it. We have a lot of pretreatment methods that we can actually use. The types of pretreatments that we know are mainly classified into physical, chemical, and biological pretreatments. Today, I'm going to show you only the results of some particular chemical pretreatments, okay, which are a solvent called N-Methylmorpholine and Oxide, briefly NMMO. It's an organic solvent which is already used in the textile industry. Simply another solvent, an acidic one, which is sulfuric acid, and another solvent, which is an alkali, and is sodium hydroxide. So I will show you the results of some materials treated with these agents before anaerobic digestion. And only to share with you some more information related to the N-methylmorpholine and oxide solvent, what I can tell you is that the important parameter when we perform the pretreatment is the choice of the right percentage of this solvent in water. Because as we can see later, we have a solution that we use to pretreat our material, which is a water-based solution with this solvent dissolved in water. And if the percentage, okay, is between 83 and 87%, we only get cellulose dissolution. If the percentage is between 76 and 81%, of course, approximately, we get swelling of the material. So the material kind of creates this sort of balloons. So it kind of expands and the accessible surface area increases. If we have a concentration of this solvent in water lower than 75% or equal to 75%, we have the swelling of the material without cellulose dissolution. And this is maybe the best condition that we can get, okay? Mainly for biogas production purposes. Other sources use, for example, higher concentration of this solvent for bioethanol or hydrogen, again, I don't remember well, but bioethanol for sure production, because it was actually more convenient to use this percentage because they actually got a higher concentration of the final product, which was bioethanol in that case. And other characteristics of these pretreatment methods are the ones that you can read here. So we can actually reduce the cellulose crystallinity, which is one of the parameters we are targeting too. We don't have carbohydrate loss, which is important because anyway, if we lose some of the material that can be valorized in the solvent which is used, we also lose part of the biogas that we can produce. The duration can be quite short. There are some pretreatments that can also get to 24 hours, 48 hours. In this case, we can also perform the pretreatment for 0.5 hours, so 30 minutes. And one of the most important things is that our solvent can be completely recovered, or at least up to 98%, with a downstream process after the pretreatment itself. So what we investigated as main feedstock in this first part of the presentation. So in our late study that was carried out in collaboration, as I told you before, with the National University of Ireland, Galway, we used three main substrates, all deriving from the agri-food industry, and quite present also on the Italian or Irish territory. We used almond shell. So we went to the supermarket, we bought almonds, we ate the almonds, and we only actually left the shells for our experiments. Then we contacted the company and we got the hazelnut skin. As you know, it's an edible part, so we can actually eat the hazelnut skin, but while processing hazelnuts, while roasting hazelnuts, industries remove this skin. And so for them it's a waste. It's pretty much a waste most of the time. And so we got this waste for free, and we perform experiments on hazelnut. Hazelnut is particularly interesting for us in Italy because we are the second producer in the world of hazelnuts, and Turkey is the first producer in the world. So it can be also quite interesting for you. And then, since part of this research was done in Ireland and in northern countries, they drink a lot of coffee. Okay, one of our target was also to evaluate the biomethane potential of spent coffee grounds. So what remains after the preparation of coffee in the bars? So my colleagues went to the bars, took these grounds, these spent grounds from coffee preparation, and used that in the laboratory for the experiments. How did we perform the experiments? So the first thing that we did was the treatment with N-Methylmorpholine and Oxide. How does it work? So this chemical can be actually purchased with a concentration of 50%. So the first thing to do is to concentrate the solution and increase it up to 73%. So we decide to use that range of concentration which allows the swelling of the material and without any cellulose dissolution. Then we performed in some Erlenmeyer flasks the pretreatment of our material, which were individually put in these flasks. So we never treated the materials together. Okay, we always treated the materials individually. So in this there was hazelnut skin, in this there was spent coffee ground, and in this bottle there was almond shell. Then we brought the temperature up to 120 degrees because only at that temperature the reaction can occur. Actually, at lower temperature, around 70–80%, this solution is actually solid. So when we were kind of storing this solution in the freezer, we could see that it was immediately becoming like rock. So it was really solid. So only at high concentration, this is effectively a solution and can be actually handled as a liquid. And we used three different durations of our pretreatment, which were 1 hour, 3 hours, and 5 hours. And after these times of pretreatment, we had to stop the reaction. So in order to stop the reaction between the solvent and the material inside these flasks, we placed the material on a kind of like filter and washed the material with deionized water at 100 degrees until reaching a clear L-weight. So at the beginning, you actually rinse the material with water, with the boiling water, and you see that the L-weight is brownish or reddish. When it becomes very, very clear, we stop. You stop the washing, and then you can actually consider that the material is ready for the anaerobic digestion purposes. So after that, we treated the material and we again characterized the material in terms of volatile solids, total solids, and whatsoever, everything COD and all the parameters that you know when you do these experiments. We started with our batch biochemical methane potential tests. So basically, we were using these serum bottles with a volume of 250 milliliters, and we filled these bottles with roughly 100 or 125 milliliters, so 40 or 50% of the volume. The substrate that we used were all sieved until reaching a particle size of 2.5 millimeters. So the important thing when we do biochemical methane potential tests is to fix a particle size, because particle size can have a great effect on the process. What did we put inside the bottle? So, of course, we used the materials, both the raw materials, so without any pretreatment, and the pretreated materials after 1, 3, and 5 hours. And a biochemical methane potential test has always to be performed with a source of microorganisms that we can actually call inoculum, and we use the buffalo manure digestate, because in our area in southern Italy, we have a lot of buffaloes because we produce mozzarella cheese, and there are many plants, anaerobic digestion plants, so full-scale anaerobic digestion plants that provide us this digestate, which is full of methanogens. So we use these matrices as sources of bacteria, mainly sources of methanogens, okay, that we partly acclimatize in the lab and then we use in our experiment. Some operating conditions were mesophilic conditions, so temperature which was maintained at 37 degrees, 45 days of observation and measurement, and the ratio between the volatile solids of the inoculum and the volatile solids of the substrate, which was 1.5. The protocol of BMP tests suggests a ratio between the inoculum and substrate in terms of volatile solids, which is between 1 and 2. Usually they use 2 in order not to acidify the system. We measured the biogas, and we measured the biogas both using some manometers to check the pressure and then to see the composition of the biogas. We used this saccharometer, which was filled with a sodium hydroxide solution. So what was remaining here in the top of the saccharometer was only methane, while carbon dioxide was trapped inside this liquid, because this liquid has a pH of 13 or 14. So carbon dioxide is transformed into carbonate. So first results. We analyzed also the chemical composition of our substrates, both the raw substrate. Here you can see the Italian term, which is grezzo, because I took the figures from the thesis of one student of mine, and we also saw then the composition of the pre-treated substrates after 1 hour, 3 hours, and 5 hours. So what we can actually see is that in terms of composition, we have mainly lignin, which is the brown bars. We have these yellow or red or green bars, which are the sugars contained in hemicellulose and cellulose, because as you know, hemicellulose and cellulose are polysaccharides. Cellulose is mainly formed by glucose or glucan chains, while hemicellulose is mainly formed by arabinose and galactose. So, and xylose also. What we can actually see is that all the bars related to almond shell are pretty much similar. If we move from a condition with no pretreatment to a condition with 1 hour pretreatment, 3 hour pretreatment, 5 hours pretreatment. So looking at the chemical composition, we could not see any important variation of it after the pretreatment. If we see instead the variation of the composition for the spent coffee grounds, we only saw a big change in terms of these compounds, which are represented here with a blue bar, which are the extractives. These are substances that are on the cortex of the material and are basically carbohydrates or proteins which are highly soluble in water and ethanol, for example. So they are easily removed by a solvent pretreatment. They are sometimes valorized into biomethane, but after the pretreatment, we lose them. So we cannot account for them for the production of biogas. But we don't see any major change in the structure of lignin, and we only saw an increase of 25% of the sugar content in the pre-treated substrate, so in the pre-treated spent coffee grounds compared to the raw one. What we saw from the analysis of the chemical composition of the substrate is that the pretreatment was particularly effective for hazelnut skin. So as you can see here, the brown bar diminishes a lot. So when we increase the duration of the pretreatment, lignin is removed by 30%, and the percentage of sugars within the remaining solid after the pretreatment increased by 110%. So this is the demonstration that we delignified our material and we exposed much more our sugars to the degradation of the microorganisms. So that's what we saw only looking at the composition, the variation of the composition of the material. Let's see if we actually had also a response looking at the biogas potential. And these are the results. So this is first the biogas potential of the biomethane potential, sorry, of the almond shell. And as you can see, we actually got a 58% increase of the biomethane potential for almond shell, moving from a condition with no pretreatment or 1 hour pretreatment to a condition with 5 hours pretreatment. But we saw that this was not due to the variation of the chemical composition, because we could not appreciate a significant variation of the chemical composition of the material. So what we realized is that actually the effect was mainly related to a variation of this water retention capacity, because we analyzed these parameters. So it's a sort of indicator of the porosity of the material. So if we move mainly from no pretreatment condition to 5 hour pretreatment condition, we have an increase of the water retention capacity, and we have then an increase of the biochemical methane potential, so that increased by 58%. This is also visible here. We can actually see how the images from scanning electron microscopy demonstrate how the structure of the material which was pretreated is much more porous, so much more bioavailable for the microorganisms to be degraded. Other two things. The first, in absolute terms, the biochemical methane potential of almond shell was always very low, because 80 milliliter of methane per gram of volatile solids is quite low, especially if you compare with some other materials, okay, which can also get to 500, 600 milliliters per gram of VS, like, for example, organic fraction of municipal solid waste, okay? So we saw that we can still do a lot with this material. This material has a lot of potential, because we might increase a lot the biochemical methane potential of almond shell. And this is demonstrated also by variation of the volatile solids, because this only decreases by 8% moving from the raw material to the 5 hours pretreated material. Quickly, on the spent coffee grounds, there was only a slight variation, if you remember, on the chemical composition, and we saw no effect on the biochemical methane potential. Okay, even though there was an increase of the retention capacity, we cannot explain well why the increase in the biochemical methane potential was not observed. Nothing much to say on the structure of the material looking at the same images, but looking at here, so we can actually see how already with the raw material, there is a decrease of the volatile solid. So there is a destruction of the organic material, biodegradable organic material in the substrate by 71%, and only 1% more in the pretreated material. So the material as a raw material is already bioavailable and is very good for the production of biogas, because we can also reach 350 milliliters per gram of volatile solid. But this is not the way to extract the extra value of this material, even though there is not much of extra value remained, because this part of volatile solids can also be, for example, lignin, and lignin remained is very, very difficult to be converted into biomethane. It's never converted, basically. What we saw here for the hazelnut skin was the major result. So we already saw that the pretreatment was very, very effective towards the chemical composition of the material, and it was also effective in terms of biochemical methane potential, because it was increased by 51% compared to the raw material. There is an increase of water retention capacity, and this can be one of the explanations of the successful application of the pretreatment. We can actually see that the structure of the material is kind of frayed, so destroyed on the surface, and this allows a much better inclusion of the microorganisms inside the material. So they find more a substrate to be degraded and converted into biomethane. And we can also see that the process occurred quite well, because the BS destruction, so the removal of volatile solids, the removal of organic material, increased from approximately 24% to 54%, moving from the raw material to the 5-hour pretreated material. Then for the second part of the presentation, I want to share with you some very nice information which is related to the use of industrial hemp for the production of biogas. So the industrial hemp has a very funny Latin name, which is Cannabis sativa, but it's not the cannabis that you're talking about. This is legal cannabis, so with the content of delta tetra hydrocannabinol lower than 1%. So can be cultivated without any sort of problems, even though there are, at the moment in EU and in Italy, some controversial legislation about the use of some components of the plant, mainly the inflorescences. Why we are getting interested into the industrial hemp, and it was something that we started within our group only a couple of years ago. We are interested in this because we can actually observe nowadays a sort of renaissance of this crop. Because, for example, if we look at the global market of the hemp, we see that it is expected to move from 4.6 to 166 billions of US dollars in 5 years. So people are again investing in these plants. Why? Mainly because it is a culture, as I wrote here, that is able to conciliate what the agri-food industry needs are and the promotion of second-generation biorefineries. So all these sustainable biological processes that start from an organic residue, okay, as raw material. Also because hemp can actually provide a very high biomass productivity. So the productivity of this plant can also be higher than 20 tons per hectare per year. It does not require much water and fertilizer, and this is very important, especially if we think about the planetary boundaries. So the use of fresh water, the imbalance in the very big biogeochemical cycle of nitrogen, for example, and also nitrogen pollution, eutrophication, and whatsoever. We don't need pesticides because hemp is an infesting weed, is an infesting plant. So if you, for example, leave a place and after 1 year you come back to that place, there might be the production of this weed, like, for example, Arundodonax or other weeds that we usually see, okay, in degraded areas or very close to the rivers. And also, it has a very high potential of carbon capture. And as I said at the beginning of the presentation, we are forced to reduce our greenhouse gases emissions in the next 10 years. And using, for example, plants can be for sure a good solution to decrease the carbon content in the atmosphere. So we were actually moved by all these motivations, and we started to evaluate the potential routes of valorization of these plants. Mainly, we can actually have the production of three, we can say, lines of products starting from industrial hemp. We get up to 10% of seeds, which are mainly used for the production of feed and food products, mainly the oil that maybe you can find in some supermarkets. Then the 60–70% of the material is made up by the hemp stalks, which are fibers and hearts inside the fibers. How can we separate the fibers, which is the green cortex that you can see here in the stalks, and the inner heart? For example, by mechanical separation, but it's quite hard. We tried in the laboratory, but it's difficult, or with maceration and then separation. So for maceration, I mean leaving the plant in water, simply in water for 1 week, and then going and basically remove the fibers from the main stalk and get this material which is inside. And then up to 30%, the weight of the industrial hemp is made up of leaves and inflorescence. Leaves have no use. Inflorescence can be used, for example, to extract some compounds like tetrahydrocannabinol or terpenoids or some other aromas, for example, but they are not finding a lot of market so far because of those contrasting regulations I was mentioning before. So, for example, the Italian regulations say that we cannot use inflorescences also, for example, for medical purposes, even though there are a lot of bioactive compounds inside this part of the plant. But since the regulators, the policymakers think that people are going to use the hemp for improperly, okay? So for smoke reasons, for example, they are not allowing also to use this for other reasons. So since they are regarded as waste, mainly leaves, inflorescence, and the hearts deriving from the separation of the fibers from the stalks, we call this material hemp biomass residues, and they constitute up to 70–80% of the weight of the material that actually is regarded as a waste. So why not valorize these in anaerobic bioprocess? And that's what we did. So we started with simple biochemical methane potential test, but now we have a PhD research line that is investigating VFA and hydrogen production from hemp biomass, and we will investigate in the next years of this PhD also the production of some polymers, for example, microbial protein, to be produced from this biomass. So we took different parts, different components of the plant. So we took the inflorescences, then we got a mix from some people providing us the material. It was a mixture of leaves and inflorescence. Then we removed the fibers from the stalks. We used hearts, retted and non-retted, so with maceration and without maceration. And then we also investigated the whole stalk, so with fibers and hearts together. And then we use some different experimental conditions. So we use, for example, the raw substrates as they are, and we then perform some pretreatment like alkaline pretreatment and acidic pretreatment. Basically, alkaline pretreatment is mainly aimed at removing hemicellulose from the material and make hemicellulose more bioavailable for the microorganisms. And the acidic treatment is instead mainly oriented towards the delignification of the material. And also we performed an extra mechanical pretreatment, which is a further grinding, because actually what we did after characterizing the material is always considered a fixed particle size. In this case, we consider particle size between 2 and 4 millimeters of the material within the digestion bottles. Then we used a ratio between inoculum and substrate of 2. And in each bottle, we used each individual hemp biomass residues, okay? So what actually we can see from the results? That the most promising part of the plant that can be valorized is the fibers. The problem is that fibers have a very important market, especially for the textile industry, because they make ropes, they make also papers, also for the pulp and paper mills, fibers of hemp are important. So it was an important result, but fibers are usually not available, are not regarded as waste. So we actually observed this, but then we concluded that would be important, for example, also to valorize the fibers. Since fibers have a different fate, we can say, we can actually consider other residues as hemp components. We then saw that the parts, so the inner part of the stalks, both retted and unretted, so macerated and not macerated, and the whole stalk produced pretty much the same. So the stalks produced a bit more than the hearts, but consider that in the stalks we also have the fibers. So basically, what we got with the stalks is a kind of average between the production obtained with the fibers and the production obtained with the hearts. We anyway achieved a production which was between 240 and 275, which is quite promising, and consider that these are results related to the raw feedstocks, without any kind of pretreatment. When we then investigated the mixture of leaves and inflorescences, we got a very, very low biomethane potential. And at the beginning, we could not describe why. So we didn't know the reason of this. Okay, we will see later. Then we performed pretreatment on different parts of the plant. So we pretreated basically the stalk, which is and the heart, which is basically the more recalcitrant part, because it's the more lignocellulosic material of the plant itself. It's mainly composed by lignin. Lignin can also actually achieve 20 or 30% of this material. We did not characterize this in terms of cellulose, semicellulose, and lignin, but if you have a look at the literature, you can actually see that lignin can also reach up to 30% of this part of the plant. And we could see that the pretreatment were not effective or only slightly effective. Anyway, plus 15% is a good result, but not actually as good as what we observed, for example, with the other materials that I showed you before. In this case, we observed a decrease of the biochemical methane potential, likely due to a loss of some material that could be valorized to biomethane, but that we lost during the use of the solvent. Also, this is actually the heart that was instead retted, so that was macerated before, and we saw that the raw feedstocks had pretty much the same biomethane potential. In this case, we can actually see that there is an increase using the pretreatment, but the highest increase was observed when we actually reduced the particle size. So reducing the particle size, as reported very widely in literature, but not only literature, also full-scale application, is an important pretreatment, okay? The problem is that the chopper that we need to use to decrease a lot the particle size of the material can be quite expensive. I mean, the lower is the particle size that we need, the more expensive is the pretreatment of the material. And this is an interesting part, because what we actually saw is that when we used only inflorescences, we then compared what only the inoculum produced, because we actually took the inoculum, we did not let the inoculum acclimatize in the lab because we only did a trial, okay? Usually when you do a biochemical methane potential test, you need to cut down to zero the production of the biomethane from the inoculum, because otherwise it means that the inoculum is ready for the tests. So in this case, the inoculum was still producing a lot, but we were not interested in that. We were only interested to see how the inflorescences were degraded during anaerobic digestion, and they were actually resulting in a production of biomethane, which was 67% lower than the sole production of the inoculum. So we understood that there was an inhibition, and that was also observed when investigating the mixture of leaves and inflorescences. And then we analyzed this much more, and we actually saw that in this material, there are a lot of compounds like terpenoids, and these are reported to be quite inhibiting for some microorganisms. And as you know, maybe methanogens during anaerobic digestion are the most sensitive microorganisms, and so in this case, they were particularly inhibited and resulted in a lower production of biogas. This is the final slide, so I think that in 50 minutes I could finish the presentation. And this is a completely different strategy that we use to increase the potential of the hemp biomass residues. We basically co-digest the hemp biomass residues with a substrate completely different, which is cheese whey, that we actually got from a farm that produced cheese from cow milk. And we tried different conditions. So for example, only hemp hearts, only cheese whey, so single digestions. And then we used two different mixtures, 70% of cheese whey, 30% of hemp, and 70% of hemp and 30% of cheese whey. What we saw is that when we mixed 70% of cheese whey and 30% of hertz in terms of VS basis, so calculated as volatile solids, so as biodegradable matter, we saw an increase of 10% of the biochemical methane potential. So the microorganisms are kind of promoted also in degrading the hemp hearts because they start degrading the cheese whey, and somehow the enzymes also attack better the hemp hearts and result in an increase of 10% of the production if compared to the calculated production. So basically what we did, starting from the production of the single substrates, we calculated the theoretical potential of the mixture, and then we compared with the experimental value, and we saw the experimental value was higher in one of the two conditions investigated. And then what we did in order to conclude this presentation was a very interesting economic analysis that you can actually read in that was recently published. And we analyzed different scenarios for both hemp biomass. We considered a low, an average, and a high scenario of biomass productivity in the future. So from 2 tons per hectare per year of production to 10 to 18 tons per hectare per year. Okay, and we then considered a low and a high scenarios also for cheese whey. That means low scenario, only 20% of cheese whey is devoted to biogas production in Italy, and 100% for the high scenario is devoted to anaerobic digestion, so to biogas potential. And what we actually saw is something which is very interesting. Okay, these are the production that we can get on the national territory in terms of million of cubic meters of methane per year that can be achieved by using this material if we get these scenarios. But this is maybe the most interesting result, because what we did is we compared the production of biomethane considering the most effective condition that we found, so this one that resulted in somehow 450 milliliters of methane per gram of VS, and then compared this, making some calculations, with the need of the private sector transportation and public sector transportation. And we saw that if we, for example, can fulfill both the high scenarios for cheese whey and hemp biomass residues, we can actually produce 300 million of cubic meters of methane per year, which is somehow 25%, 27% of the gas needed for the transportation sector. So this would be for sure a very, very important result, even though we know that in order to fulfill the achievements of the targets of the Paris Agreement, we are moving mainly towards the electrification of vehicles rather than using gas from renewable sources. So I gave you a very quick overview of these topics that we have been investigating for some years, and I'm very glad if you can have some questions that I can answer. Thank you.
Stefano, it's very clean, straightforward presentation. We may have some questions and comments if there are any.
Okay, thank you, Stefano. Nice presentation.
Okay.
Can you hear me? Okay.
Yes, Bestam, yes. Yeah, now I again see your faces.
Yeah. So, you know, biocircular economy is the most important thing for the future, considering Green Deal. So, what's your opinion? What will be the impacts on bioenergy sectors of COVID pandemic, actually?
That's actually a very nice question. So it's also a question that we should address, not with a simple question after a presentation, but with a lecture, because anyway, biocircular economy is what is waiting for us in the future. So basically closing the loops, for example, from the production of a commodity till the disposal of the waste, and by using all the possible sustainable alternatives. And for sure, what I presented here is something that goes in this direction, because we are using leftovers, waste, feedstocks, residues that can be valorized somehow, and then the energy produced, of course, can be reused for a lot of applications. The problem is that the COVID pandemic has pretty much slowed down everything. So the good thing is that we are seeing, at least we saw till last year or the beginning of this year, some benefits on the environment, because some studies report an important decrease, for example, of the carbon emissions in the atmosphere. But in terms of energy, we need to hope for all these plans that now the European Union is funding for all the countries in Europe. Because, for example, in Italy, we have a budget of roughly 200 billions of euros that we have to spend for some sectors, so transportation, renewable energy, digitalization. And so even though COVID pandemic has slowed down a lot of things, including the development, for example, of some technologies, for example, it's a good thing, because we somehow woke up and maybe realize that if we continue going in a not sustainable direction, a pandemic, an epidemic is something that can occur and can anyway kind of jeopardize our future. So for sure it has an effect on the energy sector, but it has an effect on everything. And the most important thing is to use actually these circular bioeconomy strategies, because anyway, it's always a matter of being, how can I say, kind of a football match that finishes 1-1 or 2-2. If we are sustainable, okay, with our technologies that we are going to develop, what we get is always a positive response of our earth and our environment. And if we respect our environment, we can actually promote our prosperity much better in terms of energy uses, in terms of our welfare, in terms of everything, and health. And so this is what I think.
Okay, thank you. Thank you.
Thank you. We have a question from our graduate student, Emine.
Is it in the chat? Because I cannot see it.
Emine, no. Emine, can you hear us?
Yes, thank you for your presentation, sir. I have two questions. My first question is, you mentioned many pretreatment processes like physical and chemical. So when these processes are finished, can the obtained biogas or biofuel be used directly in real life? My other question is, hazelnut skin and almond shell, which are garbage, need to be collected somewhere in order to be used as biofuel after all. So is there a project in the world or in your country to collect them somewhere?
Okay, I can start from the second question because my answers will be clear. So as I was telling during the presentation, there are all these factories that process nuts. So like, for example, walnut, almonds, hazelnuts have these residues. Okay, so consider that the first industry that provided us this material was the industry that makes that cream of hazelnut and cacao. I'm not saying the name just for not making advertisement, but it's known in all over the world. Okay, so they were giving us this material because they wanted to see if it is possible to give birth to these residues that you call garbage. Okay, because for them it's a waste. For us, it's not a waste. So it's feasible to get them. And I also know some, for example, Turkish researchers that are working on this. I don't know how they get this material, but in Italy, we have industries that can provide this to you in order to make some research because they are interested in this. So it's not something that is actually still developed at full scale, because especially in our area, so in southern Italy, we have anaerobic digesters that treat mainly manures from buffalo and cows, or also pig manures and dairy products, or some, for example, residues from the production of olive oil. Okay, so this is what we basically use in our full-scale digester. Of course, the potential of this material is very, very high, but as I showed, it needs a pretreatment. So sometimes you need to evaluate carefully if it's convenient or not, because we did some techno-economic analysis, not only on hemp, as I showed, but also on these materials, and we saw that only in some conditions, so when the biomethane is very high, the process is worth it, because anyway, you have a lot of expenses. Some pretreatment are quite expensive. The operating conditions are quite severe, and so you need to spend money for that, and then you get a profit from biomethane, which sometimes is not as equal as the expense. The first question was about, sorry, I already forgot. It was about the
treatment processes, like you mentioned, many treatment processes, physical, chemical. Yeah. So I want to learn. So when these processes are finished, can the obtained biogas or biofuel be used directly in real life? Okay. The question is this: that you first perform the pretreatment. Then after the pretreatment, you again take the solid from the pretreatment. So you need to wash it from the solvents. You take the solid, which is chemically different compared to the raw substrate, because there are modifications, for example, in structure, modification in cellulose, hemicellulose, and lignin content. And then you use this for the biological process. After the biological process, of course, you can use biomethane, for the production of thermal and energy and electricity, or injecting directly the biomethane, into the national grid of gas after an upgrading of the biogas, because the biogas is roughly 60-70% of biomethane, 30-40% of CO2, as some other gases in traces like hydrogen sulfide. They need to remove these gases, which are carbon dioxide and the other components, and then use the biomethane, so after this upgrading, as a fuel. So it's not immediately after the pretreatment. After the pretreatment, you have the biological process. You produce biogas. After biogas, you clean up the biogas. So you transform the biogas, which is a mixture of methane and CO2, into only methane. And then you can use actually methane as you want. So as a fuel, and you put in the national grid. So it comes to your home, for example, to your house. Or you can use the biogas at the plant where it's produced in order to produce electricity and thermal energy, which consider that for 40-50% need for the self-maintenance of the plant.
So because this plant, for example, is operated at 35 degrees, and you need to warm up the reactor, then you need, for example, the electricity for the pumps, you need the electricity for the mixers, and part of this electricity is generated by the biomethane itself, okay?
Okay, thank you very much, sir.
You're welcome.
Thank you, Stefano. Is there any more comments or questions? I want to ask something. You say, considering the budget-wise, you say, I mean, minimizing the particle size, it increases the biomethane potential, right? The efficiency. But you said it's getting more expensive. What is that cost coming from? I mean,
yeah, the cost is coming from the model of the chopper that you need. I can actually tell you that, okay, this is more an aspect related to a pilot scale or full scale operation of anaerobic digestion plants. So if you, for example, are in a lab, you don't consider this because, for example, you have a mincer, you have a chopper that can actually make your material to a certain particle size distribution, and then use some sieves in order to fix your particle size. You don't care about what you spend. But in pilot scale and full scale, this is very important because the operators always tell us that this is an important cost of the plant. It's not, of course, the main one, but it's an important cost because
total cost, yeah.
Yeah, because anyway, if you want a particle size of 2 millimeters, you need to buy a model. If you want a particle size of 0.2 millimeters, which might enhance the production of biogas, costs more. And so then you have to see if it's worth it or not, because if the biomethane potential is only a bit higher and does not justify the further expense, you don't do that.
Okay. Are we done with the questions? I guess everything is very clear and straightforward.
I'm happy for that. Yeah.
Thank you, Stefano. Thank you very much for.
Oh, you're welcome. Thank you very much. Really, it was very nice to
host you in further future in our campus.
Yeah, I hope so.
A presentation face to face.
Great. Yeah.
Okay, thank you very much again.
Thank you very much, Besami. Thank you very much, Murat, for organizing these very nice talks.
Thank you,
Stefano. It was a pleasure for me.
See you maybe in Italy or Turkey.
Okay, hopefully. Bye. And bye-bye to all the students. Thank you for attending.
Thank you.
Bye.